Hello, welcome back to the online lecture. Last week we studied the magnetic fields in chapter 28, right? In this week we will study chapter 29, and the title is Magnetic Fields Due to Current. Actually, we already learned a little bit about the current coming from the magnetic field, right? So this week we will study a little bit more detail. And so if you remember what we have learned last week, this week's lecture will not be difficult, okay? So in the last lecture, we learned the definition of magnetic fields, and we also learned the force from magnetic fields experienced by moving charges. Okay, please make sure that you understood that the charges have to move in order to feel the force from magnetic fields, while they don't really have to move when they experience Coulomb force from an electric field, okay? Okay, and then we learned how magnetic force can be used to design an electric motor, and we finally learned what a magnetic dipole moment is and its potential energy in a magnetic field, which was very similar to the potential energy of an electric dipole moment in an electric field, okay? And in this lecture, we will first study how to calculate magnetic fields created by current using the Biot-Savart's law, which means that we are going to use the mathematical equations to explain how to calculate magnetic fields. Okay, and then we will learn another law, which is called the Ampere's law, and this Ampere's law is very close to the Gauss law for electric fields. Okay. And then we will also learn the magnetic fields in a solenoid. And a solenoid is actually a type of coil which looks like this. So, and this is a very important device in the case of magnetic fields. So that's why we are going to learn it. And then we will finally learn the magnetic fields due to a magnetic dipole. Okay, this is what we are going to do. Before we move on, let me first discuss magnetic hand rules. These are the rules that you may find convenient when you try to remember or understand the relations between the force vector and velocity vector and magnetic field vector. We already learned that the force vector is equal to the electric charge multiplied by its velocity vector cross-producted by the magnetic field vector, right? Here, let's try to express this relation using your hands. In this figure, we have a magnet with the north pole here and the south pole here. So the magnetic field goes from right to left. So this will be the direction of the magnetic field vector. Okay. And then let's assume that this electric charge is moving up. So the its velocity vector will be pointing up in this way. And now let's use the your right hand, to represent the direction of the magnetic force. Okay. So in this figure, stretch out your hand and use your forefingers to point along the magnetic field vector. And I like this case because these parallel forefingers looks like the magnetic field lines, right? So it's easy to remember. And then stretch your thumb so that it will point along the velocity vector. And then the direction of your magnetic force vector will be the direction perpendicular to your palm. Okay. And this kind of makes sense because this is the direction along which you can apply the largest force using your hand, right? So I like this rule because it's easy to remember. And some people actually like to use the curled hand or a fist to represent the same relation, but I personally like this case using the extended hand because just like I said, it's easier to remember. Okay. And there is actually a left hand rule which was given originally by Fleming as shown here. And then it also shows you the same relation, but I personally do not like this rule because I always like to use right-hand rule. So when I was in school, actually, I made up my own right-hand rule, as shown here. But actually, it doesn't matter which one here you are using. Just pick any one you like the most, because the physics is the same. These rules only give you a convenient method to remember. So pick anything you like, which you find the easiest to remember, and then it'll give you a convenient way to remember it. Okay, and there is this right-hand rule also can be useful in showing you the relations between the direction of the current and the magnetic field around it. Okay, this is again right hand. And we already have seen this in the chapter 28, in the previous chapter, right? And we will discuss this more quantitatively in the next slide. And it was in 1918 when Oersted discovered that the current flowing in a wire produced magnetic field, and he found that this magnetic field encircled around the wire, just like shown here, following the right-hand rule. So it was Oersted who discovered the right-hand rule for the magnetic field due to a current. And this phenomena, in fact, suggests that electric and magnetic fields are fundamentally and closely related to each other, because the current represents the electric field and it always carries the magnetic field. Okay, and because of these fundamental relations, many features of magnetic fields are similar to those of electric field, although they are not exactly equivalent or the same. We will see that one by one. And finally, the Biot-Savart law is the law that tells us how to calculate the magnetic field due to a current. And this law is in fact an empirical law, just like Coulomb's law. So therefore, it was obtained by experiment and observation. And in fact, this Biot-Savart law can be mathematically derived, but it will be very difficult to understand, and difficult to follow. So here we will not do mathematical derivation, but we will just take a look at the result and try to understand its meaning. Okay, so we need a wire where the current is flowing. So we have a current flowing here, and then, like I said before, current is not a vector. So we need a different vector which represents the direction of the wire where the current is flowing. So we will use this ds vector representing the small portion of the wire following the direction of the current. And then we need to define the position where we want to know the magnetic field. So it will be this R vector will be that position with respect to the location of this ds vector. Ds is a small vector, so okay. So R vector is the displacement vector between these positions. And then we will express the magnetic field by the Biot-Savart law. Okay, so this is how the Biot-Savart law tells us the size of the magnetic field at this location. Okay, so here let's first take a look. First, this magnetic field is proportional to the current, size of the current, okay? And then it is also proportional to the size of this, or length of this wire, okay? And then it's also inversely proportional to the square of the this position vector, which means the distance between these two positions, okay? And then there is this proportionality constant. And then, in fact, there is a angle term. Okay, there is a sign of the angle between the direction of this current and then the position vector of the location, right? So therefore, this sine theta suggests that we can actually use the cross product, which is shown here. So this is will be the cross product between two vectors. The first, the vector representing the direction of this wire or the current, and then the vector representing this position. And here, well, there are two equivalent expressions. So here, please make sure you remember that this is a unit vector which has no size. Its size is unity. So therefore, we divide it by r squared as we have discussed before. But then in the final expression, we have a r vector which has a size, right? This is why now it is divided by the cube of the distance instead of the square of the distance. Okay, please make sure you understand why we have these two expressions. Okay, and then also this part of the proportionality constant is called the permeability constant, and its size is shown here. You don't really have to remember the number, but remember that actually this permeability constant itself is a very important constant in magnetism. So while you don't need to remember the number, try to remember the name, and then we use the symbol like this. Okay, and then finally let's compare this Biot-Savart's law with the Coulomb's law. Okay, take a look at this. How do they look? So in the Coulomb's law, the electric field was proportional to the electric charge, but in the Biot-Savart's law, the magnetic field is proportional to the current. But and then there's another similarity that both are inversely proportional to the square of the distance, right? And then there is a proportionality constant, which both of which contain 4 pi. Okay, and then in the Gauss law, I explained why we get 4 pi. Okay, and then but then there is another important difference. In the Coulomb's law, the electric field is parallel to the position vector, but in the Biot-Savart's law, magnetic field is perpendicular to the position vector. Okay, so there are some similarities, but at the same time some differences. Okay, and here we have an example showing how to calculate the magnetic field using the Biot-Savart's law. Okay, and in this example, we have a long straight wire as shown here, and then we want to calculate the magnetic field at the location P. And then the shortest distance between this P to the wire will be, of course, drawing the line perpendicular to it. So we call this distance R perpendicular. Okay, and this is the Biot-Savart's law we have seen in the previous slide, right? So this Biot-Savart's law does not give you the final value of the magnetic field, but it only gives you the small portion of the magnetic field coming from the small portion of the wire ds. Okay, and what is ds? In fact, in order to explain ds, you first have to define s, which represents the length of this wire or the position of the this ds. So here, for convenience, we set this location at the bottom of this r perpendicular to be the 0 of the s. At this here, s equals 0 here. Okay, and then the right side will be positive and negative. Left side will be negative of s. Okay, and then as we will be integrating following this wire, the small portion of this wire at distance s, we call this ds. Okay, this is small portion of wire which is ds, and then of course it's represented by the vector because it's the length and the direction. Okay, this blue arrow looks a little bit too large, it's misleading, but the ds is like a small portion shown here. Okay, and then the distance r is in fact the distance between this ds and then the p. Okay, this is what we call r. Okay, and then this theta, what is theta? Theta is an angle between this ds vector and then this r vector actually representing your position with respect to the position of this ds. So this much is theta. Okay, so when we try to calculate the full value of the magnetic field, we have to integrate along this wire. So this is what we are doing. The magnetic field is an integration of dB, which is small portion of magnetic field, from minus infinity to plus infinity, right? Okay, and then here, actually, whether you go to the right or left, they look the same. It's actually symmetric. So therefore, you don't have to go to minus infinity, but you only need to integrate from 0 to plus infinity, which is only on the right-hand side, and multiply by the 2, because the left side will be symmetric with respect to the plus right side. Okay. And then let's insert this Biot-Savart law here, and then this is what you get. Okay. Here, of course, the proportionality constant will come out of the integration, but at the same time, make sure you understand why this the current also comes out of the integration. Why? Because if you have a single wire, the amount of current will be the same everywhere. So it is a constant. Okay. And we have to do this integration. But here, first you have to notice that the s is the variable of integration, but at the same time we have theta, which changes when s is changing, right? So for example, when s is very small, angle theta will be almost 90 degrees, but when s is very large, the theta will be close to 180 degrees, right? Okay, at the same time, the distance r will, of course, also change, right? So here we have three different variables. So if you have more than one variable in the integration, it is very difficult. So you have to convert two variables so that all of them will be represented using the same variable. Okay, so this is what we do. First, the sine theta. Sine theta, of course, we know that sine theta is actually equal to sine pi minus theta, and in this picture, this much will be pi minus theta, right? And then what is the sign of this pi minus theta? Is, of course, if you understand the trigonometry, is simply r perpendicular divided by r, right? Okay, and then r is in fact we can again convert it and then express it using s. And then by actually, this is what we call Pythagorean theorem, right? I think everybody knows the Pythagorean theorem. So r square is equal to r square will be equal to r perpendicular square plus s square, right? Okay, that's Pythagorean theorem. So we have the r equals square root of s square plus r perpendicular square. Okay, here r perpendicular is a constant. This is the distance you want to set up so that you can calculate the magnetic field. And S is changing, but then here finally you successfully converted the sine theta using variable you want to use and some other constant, right? Okay. And then how about this r square? Well, we already have seen what is r, so therefore r square is obvious. You simply have to take the square. So you finally insert them and convert them, and this is and then finally, okay, here this is finally what you get. Okay, and here so you see that you have s which is a variable, and then r perpendicular is just a constant. So this integration can be done, and but here this is a little bit tricky because it has a power of 3 halves, right? But probably in high school you learned how you can take care of this kind of integration. And then, in fact, in this case, a trick is introducing this angle phi and get the tangent value. So tangent of this phi will be s divided by r perpendicular. So you can write it this way. So if you insert it, now your variable integration will change from s to phi. So when s is 0, phi will be also 0. And when s is very large and goes to plus infinity, and that is like this line goes almost like this. So therefore, in that case, phi will be 90 degrees or pi over 2, right? So this is why after the conversion we have integration from 0 to pi over 2, and then the integration, the variable of integration, change it to phi. Okay, and then if you follow this process, you can finally figure out that actually the magnetic field is obtained as mu naught multiplied by I divided by 2 pi perpendicular. Okay, so this process of integration is a little bit too difficult. So it'll be nice, it'll be very nice if you have understood it, but it's okay even when you do not really understood it. Okay, so because it's a little bit too difficult, so I'm not expecting you to fully understand it. But there is one thing I would like you to do. Please remember the final result. What final result? This. Okay, so what this tells you is that when you have a straight wire current carrying current I, then the magnetic field will be proportional to the size of the current, which is of course, right, and which is obvious. And at the same time, it will also be inversely proportional to the distance from the wire, right? Okay, so these are the two important things you have to remember about the relationship between the size of the current and the distance and the magnetic field. Okay, and then this equation, in fact, will be used in the next slide. This is why I'm asking you to remember this equation. Okay.